Hi friends, today we're going to talk about graphs. So graphs are going to be our very last of our major data structures for the course. They're actually extremely rich in terms of the things we can do with them, and so as a result we're going to spend many days working with them. We'll actually have one more data structure towards the very end of the class known as a trie, but as far as our key data structures, this is our last one. So what is a graph? Well, it's simply a set of nodes, sometimes known as vertices, connected by edges, and all of these connections need to be pairwise. So if we look at this, this is a graph which represents the Paris metro, and each of these nodes is a stop, and each of these edges is a connection. And we notice that each of these edges, of course, is a pairwise connection. And so we can imagine that this graph, we can say, okay, at this station, you could take the train all the way along here, transfer, go this direction, and so forth. And that's simply what a graph is. So there are many types of graphs. Two of the biggest distinctions are between directed and undirected, and cyclic and acyclic. So let me just kind of go through these here. So a directed graph is one where the edges have a notion of direction. You could think of these as a one-way street, for example. If it's a one-way street from A to B, you can only go that way. Whereas in an undirected graph, there's no notion of directionality, and in theory, we can traverse the edges either way. We also have a distinction between acyclic and cyclic. In an acyclic graph, if it's directed, there's no cycles. That is, there's no way I can take a path that leads me back to where I started, right? And so in this case, we could see that if I leave A, I can never return. Whereas in a cyclic graph, there exists at least one cycle. So in this case, it turns out we can get back to any of the nodes in our graph, but in general, cyclic simply means at least one cycle. With the undirected case, acyclic is a little different because, well, in this case, if I leave A, I can always go back. But we don't consider this a cycle, going from A to B. That would be a little silly. Instead, cyclic means there exists some path that brings us back to the same node without reusing any edges. There's a third distinction which is common, which is whether or not we have labels on our edges. So for now, we're not going to have many of these today, but in the future lectures, we'll talk about how these could be useful. And these could represent, for example, travel times along an edge, could be the length of the edge in space, it could be any number of things, right? The cost to produce this edge, and this is just a general notion. You can label these graphs with edge labels. And so it is that in some cases, there are some problems where an undirected acyclic graph is the most appropriate thing. Another where a cyclic directed graph with edge labels may be appropriate. And each different problem you want to model in the real world will require a different type of graph. So let's talk about some terminology here, be a little more precise. So first of all, we'll say a graph, as I mentioned, it's a set of vertices, also known as nodes, and a set of edges, which are pairs of vertices. So we could think of these connections as maybe just a tuple or a pair of vertices. So for example, here's a vertex, here's a vertex, here's a vertex, and here's an edge. And we could, in principle, represent this edge as the tuple containing these two vertices. Now, vertices that we have an edge between, we call them adjacent. And by the way, this figure is from the optional textbook for the course. But so if these two vertices here are considered adjacent because they have an edge between them, these two vertices are not adjacent, even though, well, look, they're close on the page. They're not adjacent because there's no edge between them. Optionally, as I noted, edges may have labels, which can, or known as also sometimes weights, though these graphs shown on the right do not have labels. So what's a path? Well, we're going to use this term path to represent a sequence of vertices which are connected by edges. And so if we look here, this is a path of 4 vertices. It's a path of 4 edges, which includes, of course, 5 vertices. And we'll say that that is a path of length 4. A cycle is going to be a path whose first and last vertices are the same. So this path here, you'll see, it goes right back to where it started, and that's a cycle. So those two terms I used kind of loosely before. These are their rigorous definition. So any graph that has a cycle is called cyclic, and if it's not, it's acyclic. And the last little term here, one that I haven't said before, is that two vertices are considered connected if there exists some path between them. So if all of the vertices, let's say, are connected, right? So if we look at a graph, this is not, so if we look at this little subgraph here, we could say that this thing is a connected graph because from any of these vertices you can reach any other. And sometimes, there's a note here, not in my terminology, these are known as connected components. So we think of this as one giant graph. Maybe this is a subway system, very strange one, where there's 3 different subway lines. Each one of these constitutes a connected component, which is the set of vertices that are all connected. Okay, so that's it for terminology. So let's delve in a little more detail in the next video and see what we could do with these things.